like 10 minutes warning kind of. So
Okay.
total it will be like 1 hour and then take. Yeah, Dipanjan.
Thank you, Sogat, and welcome everybody. After a long time, we're having an online-only colloquium, and it's delighted to have Leah Morabito as a speaker today. Leah is a professor of research at the Department of Physics at Durham University. She has been intricately involved in all sorts of activities related to LOFAR for a very long time. And her research interest broadly is radio emission from supermassive black holes in all different forms. And I'm sure we'll be hearing more about it. Just to give a history behind why we're having this online colloquium, Leah was supposed to travel to India and actually visit IUCAA in person. But unfortunately, due to global events, she had to postpone her travels. But then we were very much interested in listening to her science, and that's why we decided to go with the online colloquium. And Leah, hopefully, we can have an in-person colloquium in future.
Yeah.
Leah, please.
Thank you, Dipanjan, for the nice introduction, and thank you for those of you who have showed up for this online colloquium. I realize we've gone back to in-person things after COVID, and online participation is really, I really value that you came to listen to me today to talk to you about my work. So as Dipanjan said, I'm heavily involved in LOFAR, so I will primarily be focused on results at low radio frequencies, but we'll talk about radio in general. So today we're going to talk about linking accretion and feedback using new high-resolution radio observations in AGN. So just to make sure that everyone's on the same page before we get started, I just thought I would just give a brief review of what AGN, or active galactic nuclei, are. So this is an artist rendition of an AGN, an active galactic nucleus. This is in the central tons of parsecs of a galaxy. And we think that every massive galaxy has a supermassive black hole. And in some cases, that supermassive black hole is actively feeding on the material in the galaxy. So it's accreting material and growing. So when you have that act of accretion, you end up with a lot of different phenomena that you can see across all different kinds of bands, from radio all the way up to X-ray. So the material that's coming in is trying to accrete onto the black hole at the center, but because it has some angular momentum and everything is trying to come in all at once, you end up setting up an accretion disk, like water that's trying to go down a drain. It can't all get there at once, and so it kind of starts to swirl around. So this accretion disk collects where material is collecting and getting really kind of like close together. And so this heats up and emits in the optical to UV. And so you can see on the right, this blue line is what we see, this thermal blackbody emission in the optical to UV. Above this region, this accretion disk, you end up with very hot diffuse gas. And this emits an X-ray. There's several different components to the X-ray. I'm not going to go into those here because it's not relevant for the talk, but just to say that these things are also bright in the X-ray. When you go a little bit further out, then you start to see in the mid-infrared, the re-radiated emission from the dusty torus. So the light is coming off the accretion disk, it's hitting the dust, it's warming up the dust, and then you see in the mid-infrared another bump from this kind of like donut of dust that surrounds the accretion disk. And then, of course, in the radio, in some cases, you can get relativistic jets, which extend megaparsecs in size, so much beyond the confines of the galaxy itself. But that doesn't mean that there isn't radio emission in active galactic nuclei that don't have these relativistic jets. And so that's why there's two lines on this SED. There's things that have very powerful radio jets, which is the top orange line, and things that don't, which still have radio emission. So the process of accretion, just to give you a little bit more detail about it, there is kind of a scaling up. So as you go from low accretion rates up to high accretion rates, you have kind of transitions. So at very high accretion rates, this is what we call radiatively efficient. This is the picture that I've just presented you with. This is also known as cold mode, quasar mode, or high excitation. So all of these things where you have this geometrically thin but optically thick accretion disk. But at lower accretion rates, what happens is it becomes radiatively inefficient. So you no longer have this kind of stable accretion disk. You have something that's puffed up. You have gas that's coming down and chaotically accreting onto the black hole. And this is what we call radiatively efficient. It's also known as hot mode or jet mode or low excitation. So if you hear any of these terms during this talk, this is kind of the division there, but just realize that it is a scale. And we're even starting now to see the difference between radiatively efficient and radiatively inefficient in observations. So this is work done by a former PhD student at Durham, looking at disk SEDs and binning them in terms of their accretion rate. And so at the top, you can see this really disk-dominated black body in the green line. And then in the bottom, you see the radiatively inefficient, where the disk has almost entirely disappeared from the UV to X-ray spectra. So why do we care about AGN? And the reason is because AGN provide what we call feedback. And so feedback is how an AGN interacts with the galaxy that is hosting it, and can change the course of the galaxy's evolution. So this is just a schematic from a paper from 2018 that shows just kind of like the kind of scales that you can have this happening on. You can have biconical outflows or spherical outflows, and these can operate on small scales, so the nuclear scale only, or the galaxy scale as well. So when you have these kind of outflows, or whatever, regardless of their geometry, they can impact the galaxy. And you can either have negative feedback, which is where whatever is going on is pushing gas out and away, and then that gas is no longer able to form stars. So you impact the star formation rate in a negative way by preventing the conditions for star formation. You can also have positive feedback, and so that's the diagram here, where whatever is going on actually can compress the gas, and so then it actually can increase the chances of star formation happening by promoting the conditions that are right for star formation. So how AGN feedback actually happens is still a major open question. We don't know all of the details, and that's why it's interesting to study what's going on in the radio, because that can tell us something about these outflows or jets that can enact feedback. So we do know that feedback is happening, but really kind of like from indirect evidence. So one of the kind of main things that convinces us that AGN feedback is happening is that we see a connection between how galaxies are growing through star formation. And so you can see the cosmic star formation rate history on the left, and how the black hole accretion, the supermassive black holes are growing. And this is related to the black hole accretion rate as a function of cosmic time. And that's what you see on the right. And you can see that these two curves look pretty similar, right? So that is really, they really kind of peak around the same time in redshift. And this really is implying that there is coevolution between the supermassive black hole and the galaxy that it lives in. So there's a lot of different spatial scales that that feedback can happen on, and it can happen on all of them, but these are kind of some of the different ways that that feedback can operate. So you can have outflows or winds. These can change things in the galaxy, like the gas temperature or the pressure, the metallicity distribution. You can have jets, relativistic jets, or even lower power, slower jets. And these can change things like the gas pressure, can cause turbulence. You can also just have radiation, and this can change the ionization state of the gas that's in the galaxy, and also the temperature. And so these three different kind of like broad categories of things that happen can happen on many different scales. But radio in particular helps us trace jets that go out to the galaxy cluster scale, where you start to have an AGN that's impacting not just its own host galaxy, but galaxies around it. And then also there's something that we won't really cover in this talk, but the subnuclear scale with the things like the Event Horizon Telescope can tell us about how these jets, how accretion is working and how that helps launch jets. Okay, so on the one end of the scale, we have accretion, and on the other end of the scale, we have impacts of feedback. And so my work is really trying to connect these two things together using unique radio observations. So this is an outline of what I'll cover in the rest of the talk. So we'll talk about how we actually trace the AGN activity, so we can start looking at accretion and feedback. We'll talk about the disk jet connection, and then we'll come on to a little bit of a technical discussion of VLBI, or very long baseline interferometry with the low frequency array, and then how we're using that to break new ground in AGN. And I'll just finish up with a little bit of where we go from here. Okay, so starting off with tracing AGN activity. So if you want to trace AGN feedback and accretion, you have to trace AGN activity. Complete samples are very hard to make because AGN look different in different wave bands, and then you can have orientation effects where, for example, the dusty torus can block the accretion disk if you're looking through the torus. This is also model dependent because you have to then go from the observations that you make of whatever waveband you are to the accretion rate, because the accretion rate is really what we're interested in when we are interested in how supermassive black holes grow. On the other hand, to trace AGN feedback, you need to look at what the AGN is impacting, and that's star formation. So star formation can be measured a couple of different ways. You can look at unobscured star formation in the UV optical, also in the radio. I'm using Lyman break techniques. To look at obscured star formation, where your star formation is enshrouded by dust, you have to go to the infrared, but you can also use radio because radio passes through dust. So radio observations can trace both AGN activity and star formation and can help overcome some of the orientation effects. And so that's why radio is a really interesting way to look at this problem of AGN feedback. So to do that, we need radio surveys. So this is just kind of a summary of the different radio surveys that are out there in the landscape today, showing you resolution versus frequency. And then with a couple of horizontal lines on there for pan-stars and HST, just to show you kind of how they compare to optical telescopes. So in radio wavelengths, we are tracing synchrotron emission, which is a power law. And so you can't directly compare the sensitivity of a radio survey at one frequency to a radio survey at the other. So what I've done here in this plot is scale everything to the same sensitivity at the same frequency, assuming a typical synchrotron spectral index of -0.7. So then this gives you kind of an idea for a typical synchrotron source, how the sensitivities of these different surveys compare. So what you can notice is that you have up to a few frequencies, a few arcseconds in resolution for these radio surveys. They cover kind of large portions of the sky, and that's represented by how large those dots are, and they cover a wide range of frequencies. So normally, if you're not a radio astronomer, probably what you have heard of and you use if you are like, I want radio information for this particular source, you go to the faint images of the radio sky at 21 centimeters. So this has kind of been a really workhorse survey for the astronomical community because the catalog is there, it's complete, it's fairly easy, fairly straightforward, easy to understand, and it's been around for a long time. So this is at 1.4 gigahertz, has 5 arcsecond resolution, and a sensitivity of 150 microchansky per beam. What I've been really involved in is the LOFAR 2-meter sky survey, or LOTS, and we have day release 3 that's just come out this year. This is at 150 megahertz. It has comparable resolution to FIRST, but has a much better sensitivity of 70 microjanskis per beam. And when you take into account the typical synchrotron spectral index, that means LOTS is about 10 times deeper than FIRST. The other nice thing about LOTS is that we have, as a survey, gone and done the extra step of making a value-added catalog with optical cross matches, so you no longer have to worry about sources that have complex radiomorphology and matching them to whatever optical, mid-infrared, etc. survey that you want to use. So if you take nothing else away from this talk or this slide, I would say I would advocate that you start looking at the LOFAR 2-meter sky survey for your radio information rather than FIRST if you are looking to add radio to a multi-wavelength survey. So what are we actually seeing in these radio surveys? So let's go back a little bit in time and take a look at this figure from Kellerman et al. 1989. This is a histogram of the radio loudness of AGN in a particular radio survey. So by radio loudness, what we mean is a ratio of the radio luminosity to the B-band luminosity. So effectively, if we think back about to that AGN SED, that's taking a ratio of the power that's coming out in whatever in the radio that's being produced by the AGN versus the power that's coming out being produced by the AGN in the optical. So you're looking at like jets to disk essentially. So you can see on this figure, there are two different distributions, right? It's we're astronomers, we like to put things into different categories. And so what you can do is you can draw a line in between these two distributions and you can say, okay, great. Everything to the right of this is radio loud and everything to the left of this is radio quiet. Very clean, very simple, a very good way to identify powerful jets. The problem is that as we have made deeper radio surveys, the picture suddenly changes to this. So here you can see now that you definitely have a distribution of things at the radio quiet end, but you have this really long tail of things at the radio loud end. And this exact same division between radio loud and radio quiet is not really doing a good job. You have a lot of overlap between the two populations. So this is also a key point is that when people talk about radio loudness, you always need to know what kind of definition they're using. Because if you make a radio loud cut that's much higher, you can get a very clean but incomplete sample of things that have powerful jets. While as you make a lower and lower cut in radio loudness, you can get a very complete sample, but you're going to be contaminated with potentially these radio quiet sources. So with LOFAR, we can ask the question, do we actually see low power jets? Does this tail of radio loud sources that you see in this figure here actually just carry down on into the radio quiet population? So this is using the LOFAR 2 meter sky survey deep fields component of the wide area survey. This was a study that looked at simulating the population. And they simulated the population assuming that every single galaxy could have two components for its radio emission, star formation and AGN activity. And then what they did is for the AGN activity, assuming its jets just come up with a power law distribution that goes from low powers all the way up to high powers, and then you simulate the entire population. By doing this, they were able to reproduce things like source counts and the radio loud fraction. And so on this figure here, you can see the simulated data points. You can see radio loudness, and this vertical line shows the cut between radio quiet to the right and radio loud to the left. And you can see the ratio of the AGN to star formation in these sources. So, and that is where they are equal. So up in this upper right-hand corner, you are absolutely dominated by AGN. These are your canonical radio loud sources, but these are the AGN dominated sources. So where the radio emission is dominated from the AGN. And you can see that there's this quadrant here where you have many, many sources where the radio emission is dominated by the AGN, but they are not caught by our radio loud classification. So the question really is, what is going on in these sources? Are they low power jets or is something else going on? So there are several different options, and this is a figure from Francesca Pinessa's review in 2019, just kind of summarizing the radio emission mechanisms that could be happening in these radio quiet AGN. So we're not going to talk about the corona because this is really something that you would see at much higher frequencies than we're discussing today. So the first option is jets. It could just be that these are a lower power population of jets. So rather than these like very highly collimated, very large sources that you can see on the right there, they would be lower power counterparts to that. Another option is that you have AGN winds that are going out and shocking the gas. And so this shock, these shocks fronts produce synchrotron emission. And there have been a couple of models that have started to predict the kind of levels of radio emission you would get from that. And it could be possible that the radio emission in these radio quiet AGN is due to winds. The final option is just star formation. These are still galaxies. They still have stars that are forming, regardless of whether they have an AGN in the center. So that's another option for the radio emission and radio quiet AGN. But the point is that we don't actually know what is the dominant radio emission mechanism or what controls whether you have star formation or whether you have jets or whether you might have winds. Okay, so let's talk then about the disk-jet connection. So we can ask the question, do jets explain everything? So this is a figure from a paper in 2019 that shows the wind column density. So this is the outflowing wind from an AGN versus radio loudness. And you see a very nice anti-correlation, right? So this is, the picture here is that you have an AGN can support a disk that has very strong winds that are coming off of it, or it can support a jet, but not both at the same time. And so that's this kind of figure here, right? So there's this kind of thought to be this, maybe there is a connection between the jets and the winds, but when you can support a strong jet, you cannot support strong winds and vice versa. So this is not necessarily something that we see supported with newer data. So here again, we're looking at modeling of we're looking at the SED, not modeling, sorry, we're looking at the SED for things with strong disks and things with strong disks and things with weak disks. And what you can see here is that here you have the massive disk emission from a strong disk, and here the disk is much weaker. But what you can see here is that if you add in the radio information, which is the black star, it doesn't really change between things with strong disks and things with weak disks. So this is really kind of calling into question whether or not this scenario is actually appropriate. Right. So really kind of also looking at it in a different way. This is work that I've done with Amy Rankin. So she looked at the carbon-4 emission and looked at how the radio detection fraction changes and how the radio detection fraction and the radio loud fraction changes across the carbon-4 emission space. So carbon-4 blue shift is thought to correlate with how strong an AGN wind is. So you can think of going right on this plot as being more wind or disk dominated. And you can see what happens is that although your radio loud fraction goes down, so to the left, if you have weak winds and weak disks, then you expect a strong jet, and you can see the radio loud fraction is high there. And as you go to the right, that radio loud fraction drops as your disk becomes becomes stronger. But if you look at the radio detection fraction, you can see that this just goes up. So there's something that's going on. The radio emission is correlated with this disk wind, and it is increasing in frequency, even if not in radio loudness, as you go to stronger disks. And then I had a former PhD student who looked at carbon-4 broad absorption lines in quasars. So these broad absorption lines give us information, direct information about the outflowing material in the disk winds, and showed that the radio is linked to the absorption profile for these. So the absorption profile is different if you have radio detections versus no radio detections. So there really seems to be some connection between the radio and the disk winds. Okay, so everything I've showed you so far is just results from the radio surveys that we already discussed. But now we want to talk about how we push this further, and that is using very long baseline interferometry with the low frequency array. So to give you a brief introduction, here is LOFAR. It is an international telescope, so we have stations spread all across Europe. It operates between about 10 to about 240 megahertz. There's a very large fractional bandwidth of 48 megahertz at a time, and you have a very wide instantaneous field of view. LOFAR is comprised of dipole antennas, and so it's a phased array, but that means that you have multi-beaming capabilities. And here's just to show you what the two different bands. The low band antenna is just these very simple wire dipoles. The high band antenna is a little bit hard to see because it's just supported in styrofoam, but it's this very thin metal bit is part of the antenna. And so these phased arrays are really fantastic for looking at very large areas and with a very large instantaneous field of view. Okay, so the really cool thing about LOFAR, though, is these international stations. So most of the kind of like standard LOFAR operations have historically been using just the Dutch stations, which provide short baselines. And here on the left, you can see resolution versus frequency. So the LOFAR 2-meter sky survey, for example, at about 150 megahertz has about a 6 arcsecond resolution. If you go out to kind of intermediate, like just including German stations, then you start to get to a couple arcsecond resolution. But if you go out to what we call LOFAR VLBI, very long baseline interferometry, then all of a sudden you get 0.3 arcsecond resolution, and you can beat what you can do with the best kind of adaptive optics on optical telescopes on Earth. So this is a factor of 20 increase in resolution between the short baselines and LOFAR VLBI. And factor 20 sounds like a really big number. So let me just kind of give you a little visualization. Let's pretend this image up here in the top left corner is an image that was taken with the Dutch stations. If I increase the resolution in the image by a factor of 20, then all of a sudden you can see all of the detail. So before you couldn't tell what was going on, now you can see it's my dogs. There's 2 of them, they're sitting on chairs, they're outside. You can see all of this detail. And that is the increase in resolution we get by going out to the LOFAR VLBI baselines. So here's just a little image of what that actually looks like for real radio data. So the GIF here is fading from Dutch station resolution to international station resolution. And then you can see on the right hand here, this is what it looks like compared to optical. So here you have an optical galaxy. Dutch stations just tell you there's radio there, how bright it is, but with the international stations, then all of a sudden you can see all of this kind of sub-galactic structure in these this source, which is just absolutely phenomenal. The really nice thing about LOFAR is the dynamic range of spatial scale. So you don't just get a high resolution image or a low resolution image. You can take your calibrated data, you can make a 0.3 arcsecond resolution image using the international stations. From the same data, you can make a 6 arcsecond resolution image, you can make intermediate resolution images, you can make lower resolution images just by selecting the baselines you're using to image. And the really nice thing about that is because it's all from the same data, you don't have to worry about systematic differences between measurements from different telescopes. 0.3 arcsecond resolution also gives us accurate source identification, classification, and cross-matching. And so here's an example of a source from LOTS, which we thought was a single source that looked like kind of a narrow angle tail galaxy. But when you go to 0.3 arcsecond resolution, all of a sudden you understand that it's actually 3 different sources. You have an FR2, you have an FR1, and you have a point source there. And the nice thing about that is now you can associate the radio emission with the correct galaxy. So whereas before you might say, oh, all of this radio emission belongs to probably something that's not even the host for one of these 3 sources, now you can pinpoint exactly where the optical or near infrared counterpart is for each of these 3 individual sources. The really great thing about LOFAR is that you get a wide field of view. So this is the Booties field, which is actually now published. And so with this high resolution imaging, 0.3 arcsecond resolution, a single 8-hour observation gives you over a 6-degree square field of view, which is just absolutely phenomenal. The field of view is actually much larger if you use just the Dutch stations, but for the high resolution imaging, it's limited by the physical size of the international stations are a little bit bigger and the beams are a little bit smaller, and then also bandwidth and time sparing. Those are really technical things. If you don't understand them, you can ask me later. But of course, doing this high resolution imaging is very challenging. So there's many challenges at megahertz frequencies and doing this kind of imaging. The ionosphere is our biggest problem, right? Because it requires that we do directional dependent calibration. So we can't just find a single correction for our entire field. We have to find corrections in different directions. Data volume is an issue. So the data sets are 4 to 20 terabytes per observation. The remote and international stations are on different clocks. And then when we started, you can see our workflow when we started looking at this in 2014, which has quite a few here there be dragons there. And we didn't even know if there were good calibrator sources at these frequencies, at these resolutions, to be able to do the calibration. And then the final thing that really we had to come to grips with is that when you have such high resolution, your sources look very different and your signal to noise decreases because the amount of flux density that is in a single beam element, which is what you need to calibrate on, is less than if you're taking the flux density over the entire source. So there's a review of all of this if you're interested in a review that came out last year, A Decade of Sub-Arcsecond Imaging with the International LOFAR Telescope. So just to briefly touch on the biggest issue that we have with calibrating LOFAR data, and this is really the ionosphere. So this shows you phase versus frequency, and there's two kind of like main effects here: clock, which is linear with frequency, and ionosphere, which is non-linear with frequency. And the ionosphere really ramps up in the LOFAR band, and this really dominates our phase errors. So the clock values are very easy to solve for. Actually, we've done a lot of work, and we really know that we know how to do this very well. But the ionosphere really dominates the phase errors, and because this is not only nonlinear with frequency, but it's also direction dependent. It makes it really, really challenging. So we have used fringe fitting algorithms before. So if you're familiar with VLBI, that's kind of standard for other VLBI arrays. But fringe fitting algorithms are unable to cope with non-dispersive so fringe fitting algorithms until only recently have only been able to do non-dispersive delays. So phase linear with frequency, which just does not work with LOFAR. So we had to develop whole new techniques to be able to deal with this. So we have done that, and we have built what we call PILOT, the pipeline for the International LOFAR Telescope. And so this kind of has two main methods or streams. And so it does what we call postage stamp imaging. So this is relatively computationally cheap, has a good application for wide surveys or individual sources. And so this is just doing calibration in the direction of whatever sources you pick in the field. You can also do the wide field imaging that I described, but this is very computationally expensive. At the moment, we've only really done this for deep field surveys. So both of these are packaged into a single software project, which is PILOT. This has pre-processing that's integrated into calibration for the Dutch stations. It can produce postage stamps and then also produce high resolution images at kind of at the highest resolution, then at intermediate resolution images. This will run end to end without requiring human interaction in most cases, which is absolutely phenomenal. But to do the full wide field, you still need about 50,000 CPU hours. But we are currently profiling the pipeline and hoping to get this value down. Oh, and just to say that I'm chair of the LOFAR VLBI working group, and this is a collection of people that have put into a lot of work into PILOT over the years. And it's really been very, very fun and to build this kind of phenomenal tool with all these wonderful people. Okay, so that's an introduction to LOFAR VLBI. So now let's talk about what we're going to do with it in order to really advance our understanding of radio emission and AGN. So something that I've thought of during my PhD actually, and then had to wait for the data to catch up, is doing unique identification of radio emission from AGN. So the idea behind this, you may have heard of brightness temperature identification of AGN before, but the idea behind this basically is that brightness temperature, which is proportional to surface brightness, star formation has an upper limit to what it can produce. So you have star formation that's producing radio emission, but it can only produce so much surface brightness, and so that provides this kind of limit here. So this is often parameterized as brightness temperature, even though that's a non-physical temperature. It's just the temperature that a black body would have to have to produce the surface brightness that we see in the radio. But we know the radio is not thermal emission. So the key thing here is that this limit for star formation is frequency dependent. So at 1 gigahertz, you require milli-arcsecond resolution. So people have historically done this with VLBI instruments like the Very Long Baseline Array or the EVN, the European VLBI network, for example, and those have very, very small fields of view. At 144 megahertz, LOFAR frequencies, or 150, you can do the same identification with just 0.3 arcsecond resolution, which is just great. And the main kind of thing here that is really, really cool is that you only need flux density and size information to do this AGN identification. So you can imagine those wide fields of view. You can, as long as all you have to do is make the radio measurements, and then you can pick out the AGN, even in sources where they are radio quiet. So the kind of state of art wide field VLBI beforehand has been done by groups at Manchester. So this is EVN observations of the Hubble Deep Field. So 1.6 gigahertz, you get milli-arcsecond resolution and a 5 arc-minute squared field of view. So in this kind of like pioneering wide field surveys, they identified 3 AGN. By using clever techniques to do multiple simultaneous phase center observing, you can expand this wide field to about a couple hundred arc-minutes squared. And here across this field, you can identify 31 AGN. So this is on source time of about 17.5 hours and using brightness temperature to identify AGN in the field. For comparison, here's that orange square is the size of the EVN field on the right there. And the purple square is what you get with a single LOFAR observation. So taking ALASN1 as an example and combining 32 hours together, you get a field of view limited by the multi-wavelength coverage there, just so we can compare our radio identifications with other things. But with 32 hours, you now get 1,500 AGN identifications using brightness temperature and the total flux density information, which will be critical in a minute. So this is a huge improvement in terms of source statistics of what we can do. And just to give you a little picture of what's going on in this ALASN1 field, these are the images of some of the final sources at the various different resolutions that you can then image from the exact same data. So because you get imaging at these different resolutions, what you can do now that you cannot do with VLBI instruments at gigahertz frequencies is you can actually separate AGN activity and star formation. So the idea is you take your 6 arcsecond image of a source and you take your high resolution 0.3 arcsecond image where you've identified AGN emission, and you can subtract that AGN emission from the total emission that you see in the low resolution image, and what you're left with is the star formation. So you can do this then for more than 1,000 sources in a single field of view from the exact same data, so you don't have to worry about systematics. And this flow chart on the right just kind of shows you a little bit of how we can separate the radio emission in these sources, that we can separate the total radio emission into AGN emission and star formation emission. And then what you can do with that is really interesting, because now you can start to make radioluminosity functions, but instead of using multi-wavelength overall galaxy classifications where you say, okay, this galaxy is an AGN galaxy, it belongs in the AGN category, and this galaxy is a star-forming galaxy, it belongs in the star-forming category. Now you can separate out the radio emission in composite sources, and you can say, this is all of the radio emission from AGN activity, regardless of what galaxy it's in, and this is all of the radio emission from star formation, regardless of what galaxy it's in. And that's what you're seeing here. This is multi-wavelength galaxy classifications, and then radio by physical process, AGN activity or star formation. And then you can compare these two by dividing one by the other, and out pops a contribution of 50% more radio emission from AGN activity than we previously expected. So this is just showing that there's a lot more AGN activity then we are measuring, we've missed this population completely until now. So where is that extra radio emission coming from? It's mainly coming from radio quiet AGN on subgalactic scales. So in the Lockman hole, I looked at this and saw that about 32% of radio quiet AGN have these high brightness temperature identifications, 20% of star-forming galaxies, and then 61% of the unclassified sources. So there's a couple of, I have a postdoc and a former PhD student who have looked at kind of these, where this radio emission is coming from in radio quiet sources like red quasars, and also AGN with O3 outflows. And really they are showing it's happening on galactic scales. Okay, so where do we go from here? In the last kind of few minutes, I just want to say like what's coming up. So I've already introduced you to the LOFAR 2-meter sky survey, but we are going back and we are post-processing all of the data, which has been up until now only processed using the Dutch stations, but international stations were included in the observations for many of the pointings. And so with my postdoc Roland Timmerman, we are now carrying out the LOTS high resolution or LOTS HR survey. So we expect an internal data release, actually probably earlier than late this year, probably within the next month. So by post-processing LOTS with the international stations, we move this point on the survey, in the survey landscape, down to comparable resolution with the Hubble Space Telescope wide field camera. So we're not processing everything in LOTS. So if you remember, I told you that the pipeline that we've developed is very computationally cheap for just looking at kind of small postage stamps around individual sources, and that doing the full wide field high resolution imaging is very computationally expensive. And so for LOTS HR, what we are doing is we are picking everything that is above 10 millijanskis in LOTS, and we're following that up with a postage stamp image. So if you have a comparison with other surveys, you can see that the sources per square degree is not very high, but the really nice thing is that this 10 millijansky selection is what we are using for Weave LOFAR. So Weave is a spectrograph, an integral field unit on the William Herschel telescope, and we have a program where we are following up everything with above 10 millijanskis to get a spectrum. So everything that is above 10 millijanskis in LOTS will ultimately have a high resolution image and a spectra to go with it, which is really, really cool. And just to say that I have a master's student who's working on using LOTS HR to quantify to characterize the morphology of red versus blue quasars in a sample from our first data release, which is really nice. And she's actually shown that this excess radio emission that we see in red quasars is likely due to jets. So LOTS HR is on the horizon, and we're processing data that's already been taken. But in terms of new data, LOFAR is currently going through an upgrade. So LOFAR, the new LOFAR will be called LOFAR 2.0. And it's mostly a back-end upgrade, which enables the use of all dipoles in a station, simultaneous LBA and HBA observations. At the moment, we can only do one, and a single clock for all stations. So I'm co-leading a project called LOFAR Enhanced Network for Sharp Surveys. And this is a project to basically procure the hardware and then also work on the software to enable the upgrade, and there's a focus on centralizing maintainable pipelines. So taking Pilot, which is community developed, and being able for the community to still continue development, but for Astron, who runs the observatory, to use Pilot and offer it as a service to end users. So along with this upgrade to LOFAR 2, there are LOFAR 2.0 large programs. There are 15 programs proposed, a 1 + 4 year timeframe. So that first year is kind of like commissioning, testing out. Not all programs will start, and then programs will run for about 4 years. About 2.5 factor over subscription, and we should get verification reviews early this year. So I'm co-leading along with Philip Best at Edinburgh a LOFAR 2.0 large program called LOFAR 2.0 Ultra Deep Observational, or LUDO. This will be 32 hours on 3,200 hours on about 4 square degrees of the Euclid Deep Field North. And this will be the deepest radio survey ever. So just to compare with other surveys, here's resolution versus hours per square degree. So we will spend the most hours per square degree out of all the surveys, but we will also be much deeper than anything else previously. So this is in the Euclid Deep Field North, so you can see the Euclid resolution as a horizontal line there. And then surveys where you can do AGN identification with brightness temperature are circled with green. So LUDO will have it all. It will have resolution. We'll be able to do AGN and star formation separation. It will be super deep, which means we can go out really far in redshift. So in LUDO, we're expecting to detect about 75,000 sources per square degree, which means we'll see Milky Way-like galaxies out beyond redshift 4 and the brightest AGN out to about redshift 6. And kind of in preparation for that, we are Jurjen de Jong, who's a postdoc who's been working in the LOFAR VLBI working group, has been working on creating the deepest ever high resolution LOFAR image, which is using 200 hours on the Euclid Deep Field North. And you can see here how the improvement you get from 32 hours to 200 hours, and LUDO will just be another order of magnitude better than that. So LUDO will enable the first simultaneous measurement of cosmic star formation and black hole accretion histories from a single tracer and the same population of galaxies. So you get rid of a whole lot of selection effects that impact our measurements of the cosmic star formation history and the black hole accretion history. And just to give you an idea of how we're doing at the moment, this is currently the ratio of black hole accretion to star formation cosmic histories that people have proposed using different AGN models. And you can see that our AGN models aren't getting it right, okay? And so there's a lot of range in what you can get with these different models. And so we really need to have better observations where we've actually cleanly picked out AGN emission to be able to help inform the models and do much, much better than this. So getting it right requires work, because once we've identified the AGN, we have to ask the question, is it a jet or a wind? So just to present you with this idea, which we've started working on, but we don't really know yet. So we do care because these models depend on how the AGN is coupling to the gas and on what scales. And so this is some work by Meenakshi that looking at jets versus winds. You can see that jets and winds can have very similar morphological characteristics. So we really need something else to be able to help us to distinguish between what is going on in these AGN in this radio emission that we've identified as AGN activity. Polarization features are different, so polarization can help us out here. Spectral index can also help us out. We expect steeper spectral indices from winds, which is very nice. So polarization and spectral index information can be quite useful there. And this has been seen actually by a PhD student at Durham who's looking at red quasars again and seeing that there's this subpopulation of red quasars which really do have this steep spectral index, which might come from winds. So to go from observations to accretion and information is really not a solved problem. So we need radio spectral index simulations, multi-wavelength information, all of this to help make advances. And then also we have to think about the fact that peak spectrum sources may have their jet powers underestimated if you're just making a measurement at LOFAR frequencies where you have absorption that's taking out the actual emitted radio emission from the jet. So to help us make advances in this, we need spectral information somehow. The low band antennas can potentially give us this as a complement to the high band antennas. I did some work on high resolution imaging at like 50 megahertz in my PhD. And most recently, Henrik Edler, who's a postdoc at a research fellow at Astron, has been working on doing this for wide field applications for the LOFAR low band antenna. So under an arcsecond in resolution, but wide field across the area at about 55 megahertz, which is really phenomenal. Polarization can also help us out, right? So we have a survey at 20 arcsecond resolution, which gives us polarization information, but you can have a lot of beam depolarization. And so at 0.3 arcsecond resolution, you can get kind of source, you can combat depolarization and also see what kind of components things are coming from. These are total intensity images, but Vijay Mahatma has been working on doing the polarization, and here you can see the polarization, the linearly polarized intensity in this source. So we're currently incorporating this into Pilot to make it a standard data product if people want it. So finally, simulations can help us out. So cosmological simulations are starting to incorporate different feedback modes, although they are inconsistent with radio observations. And so there's a lot of work to do now with all the new radio surveys that we have comparing with simulations. We can also look at semi-analytic models to try to see if we can update anything or if they can help us help inform how we interpret our radio observations. And then, of course, detailed jet and wind simulations are telling us that about feedback that's happening at different scales. So, for example, Tiago Costa has seen halo-scale winds, and so these detailed simulations could be really helpful in interpreting our radio observations as well. So the upcoming radio landscape, just to finish, LUDO will be really transformational and in helping us link accretion and feedback, but it will also be critical to have other information. So broadband radio SEDs, polarization, simulations, and multi-wavelength data. And so this is kind of what we have currently in terms of resolution versus frequency for different instruments. But of course, the SK is coming online, and potentially also an Australian Pathfinder telescope called Lambda. And you can see that we start to fill in some of the frequency and resolution space there. So yeah, just Lambda is the low frequency Australian megameter baseline demonstrator array. It builds on SKA low and hopefully gives SKA low some actual resolution, which would be comparable to LOFAR 2. Okay, so just to summarize, I don't really have like a point-by-point summary, but to kind of give you some take-home thoughts. So current state-of-the-art VLBI with LOFAR is really enabling us to do a lot in terms of studying previously unidentified radio emission from AGN, and also crucially separated from star formation in statistical examples. LOFAR 2.0 will be really unique in the upcoming radio astronomy landscape and really game-changing with programs like LUDO, to explore the link between accretion and feedback. And it's really exciting to be part of this at a time when there's so much in terms of advancement in high resolution imaging with LOFAR and what we can do with it. So I'll stop there and very happy to take any questions. Thank you.
Okay. Thank you very much, Leah. So I'll now ask the participants to raise their hands and then we can take questions.
Everything was totally clear.
Or we don't know how to raise hands. I'm trying to raise a button actually. Zoom has changed things.
All right.
So,
There's a question on the chat.
okay, Prathamesh, you can unmute yourself, or maybe I can.
Yeah, I mean, I can read the question.
You can. How does jet duty cycle affect the aging contribution?
Yeah, I mean, that's a great question. So it definitely will, and especially at low frequencies where you're seeing very long-lived electron population. So you're getting really an integrated measurement. So if an AGN turns on and then turns off and then turns on again, you might be seeing both of those episodes contributing to the total integrated flux density or radioluminosity at low frequencies. So this is that's not necessarily a problem if you're just trying to identify AGN, but if you're then trying to go back to things like jet power and accretion rate, then you're in trouble because you don't know how many episodes of something has had. And so you might think that if there were actually 2 episodes, but you only account for 1, you might overestimate the jet power, the accretion rate. So this is a problem we have not yet solved. So we are at the point of starting to identify this AGN emission that we've previously missed. In very large sources like FR2s, like Hercules A is a great example where you can actually see evidence for different episodes in the radio emission. So for things like that, you can kind of get the answer, but for these kind of like lower luminosity, lower power sources, it's something that we will have to contend with. And I don't know how we will do that yet. That's a very good question.
Right. I see Dipanjan, you raised hand. Since you are a co-host, I think you can unmute.
Yeah, I was just trying desperately to search for the raise hand button because it changed things. Now I could figure out it's under React. I didn't want to give up any weird emoji sign. Yeah, thanks, Leah, for this excellent overview of this VLBI, and what's more to come is what very is interesting to look forward to. I had a question on the other side, actually. Then I usually advocate for AGN questions and berate people because they miss out on AGN. But let me switch sides and go to the star formation bit.
Yeah, okay.
So, what you're doing is fantastic, that you're trying to isolate the AGN amongst the ruin of star formation. Now, with the very high resolution that you have, and I guess now you're also pushing back to higher redshifts, can we also map out the radio distribution in the star forming regions in much more detail, and then find out how, there's this open issues about the FIR radio correlations. Can these surveys that you're planning to do address some of these questions in some way?
Yeah, absolutely. I mean, I think this is really, so Philip Best is quite interested in the star formation, and we collaborate very closely together. I mean, we're co-PIs of Ludo. So that is the other part that I didn't really focus on today. But yes, you will see kind of resolved star formation, not necessarily individual clumps, but you can see like clumpy morphology and higher redshift galaxies with Ludo, and that is something that we are planning on doing with the data. I think what would be quite interesting, and if I ever have time, is just to take this kind of separation between AGN and star formation, and then take those radioluminosities from star formation and integrate them. But I think we need slightly deeper data because there have been some predictions, for example, from the Meerkat Deep 2 field, that where the radio cosmic star formation history is a little bit higher. And I think that if we remove AGN from the emission from the star formation, we may be able to just fix that. And it could be this low luminosity population that's in 20% of star forming galaxies, that's actually just making those measurements just seem to be a little bit high. So yeah, there's quite a lot to do there, and yeah, it will be really exciting to see that.
Okay, I have one more question, but I see more raised hands. So Saurabh, maybe I'll come back with my question later on. You can ask that.
Okay. So Raghav, can you unmute yourself and ask your question?
Am I audible?
Yes.
Yes.
Yeah. Hi. Can you please show the last slide of your presentation? Just the last slide I want to ask.
Yeah. Let me just pull it up. Right. So this one?
Just a second. The one which had the difference between 32 years and 32 hours and 200 hours time resolution, I think.
Yes. This one?
Yeah. So can you show the more? Yeah. So what is this four-way outflow that you are seeing in the center? Can you explain what is this?
This is the fireworks galaxy.
Okay.
And it's actually a superposition of two galaxies. So you have an FR2 that's going this way, and you have an FR2 that's going this way.
So it's like a cross. It's looking like a cross. Okay.
Yeah. This is a very well studied galaxy. It's just really spectacular at LOFAR frequencies. So it's really a nice image to show. But yeah. If you're interested in it, you can look up the Fireworks galaxy, which is actually two galaxies. Yeah.
Okay. Thank you.
Okay, Balpreet, can you unmute yourself? Yeah, you can ask. We cannot hear you. Balpreet, we cannot hear you. Okay, you can just type your question. Yeah. That works. Dipanjan, would you like to ask your second question?
All right, I'll go ahead till while Balpreet tries the question. So, Leah, this is again related to the AGN luminosity function. And in 2019, there was a nice paper from Philip Best's group by Sabatar 2019 that showed that as you lower the radio thresholds, it's almost like 100%. All of them have some sort of a non-thermal, non-star forming core. Now, with a kind of large scale...
Sort of. A radio loud AGN, not necessarily a non-thermal non-star forming core. What they did was based on radio loud classifications.
I see. So this is, I'm talking about the Sabatar 2019 paper, right? Yeah. So, but all of them were radio loud galaxies? But the power, like the watts per hertz, radio power is, as you go down to lower values, I think 10 power 21 or so, it just reaches 100%.
Yes, but it was based on the radio loud population.
I see. So now with these new surveys you're planning, can you revisit those estimates? Like my question is just, and then can you, because there was a thing in the community, maybe we are missing out effect of radio AGN or, in low power systems. What kind of results are we expecting from this deeper surveys then?
Yeah, I mean, so I think, okay, so the first question, can we redo the Sabater et al. Work with the, I think that would actually be quite a nice project to do, to just redo that, but using brightness temperature AGN identification in addition to radio loud. That would be quite straightforward and might be quite informative on the incidence of AGN in galaxies of particular stellar mass. And then the second question is basically, what do we expect from this lower luminosity population as we go deeper? I think the answer is we don't know yet. So I think LOFAR is kind of really on the cutting edge of going that deep. And we have done quite a bit of work as a collaboration on things like, there's been a lot of work on looking at the radio excess population, so LERGs and HERGs. And as you go deeper, what do you see? So Rohit Kandapalli, who's a fellow at Durham, has done a lot of work on looking at the kind of like galaxies that HERGs and LERGs live in, and finding some unexpected things like star forming HERGs, and that there is a more complicated connection between the accretion rate that we see and the type of source that we see in the radio than we previously thought. So I think we will find out more, but I don't know exactly what we'll find because
I understand. What I was wondering was, have you done any pilot study before you go to the full-scale survey, just to see?
So that is what we're doing with the LASN1. So that data is has been all processed now. So 200 hours, that's the most that we have with international stations for the LASN1 field. And so we are working on essentially correlating the different radio sources at the different resolutions. So you get a catalog at 0.3 arcsecond, but how do you know which source those, all of those things belong to at 6 arcseconds? So we're working on, I'm actually, that's what I'm doing at the moment. So Urian has done all of the data processing, produced the catalogs, and now I'm matching across the different resolutions to provide a single source catalog. Once we've done that, then we can start doing science. So we'll have an internal release for the collaboration to give people a little bit of a head start. But that will be an excellent pilot study for Ludo, for example. In terms of iLots, we also have some data in the H-Atlas area where we can start to process the data as if it were iLots observations. And Tim Shimwell is starting to work on that, but hasn't gotten very far yet.
Thanks, Leah. Yeah. Wonderful talk. Thanks.
Thank you.
Right. So, Bulb, can you read, Leah, the questions that Bulb posted?
Yeah. So the first one is, can we say something about positive feedback and negative feedback from the disentanglement between star formation and AGN? So I think we could, but I mean, the data exists. I haven't looked at it yet. Part of the problem with positive and negative feedback is that timescales may be different. And so there has been some work to show that, like, looking at simulations and basically saying that you can't necessarily really tell between positive and negative feedback if you look at observations, just because of the timescales that things are happening on. But I mean, very easy things to do would be to take a look at this hidden AGN population and look for multi-wavelength tracers of like enhanced star formation or depleted star formation. But the data exists, but I don't think anybody has done that yet. And then the second question, any idea about the dependency on changing look AGN on the history of you? Oh, no, I haven't gotten into changing look AGN, although there is someone at Durham who does look at that. And so maybe we will ultimately take a look, but yeah, I don't know a whole lot about changing look AGN. So sorry, I can't answer that question.
Okay, any other questions? I have a very quick query. So you said that you are going to follow up with Weave for your sample of this brightness temperature selected agent.
Yeah, so actually Weave will, so LOTS has a wide area component, which is the entire northern sky minus some parts of the galactic plane. And for everything that is above 10 millijanskis, we expect a spectrum. For the deep fields, we are targeting everything to a much lower flux limit. So we probably won't get absolutely everything in the deep fields with Weave, but we're going to try.
So my question is like, what is the redshift that you are talking about for these objects that are showing nearly 50% or something? You quote that the signature of. So what is the?
That's a great question. Let me see. Do I have a? Just looking to see. So I did. Yeah. Just share. Backup slide. Okay, so with the current data, these are the radioluminosity functions that we get in terms of redshift. So this is for AGN on the left here and star formation on the right. Ignore these plots; those are from simulations. But if you're interested in the the redshift range. So we kind of are not getting down very far. So we're kind of like complete up to luminosity, very high radioluminosities for things that are going out to about redshift 2.5 is what we can currently do in terms of what we have in the deep fields at the moment. So this is something that we can hopefully do better with in Elias when we have deeper radio data. But we will also probably need some deeper spectroscopic data. So Weave, I think, will hopefully help us out there. But at some point, we're just going to have to rely on photometry for things above, let's say, redshift 4 to 5.
Mm-hmm.
Does that answer your question?
Yeah. So I was just wondering, like, whether you already have some of the sources already observed by SDSS or something like that, and then what do you know about that?
Yeah. So in the deep fields, especially, we've done Rohit and Ken Duncan have compiled as much multi-wavelength information as possible, which includes getting as many spectroscopic redshifts as possible. So it's not very complete for the deep fields, and Weave will really help out with this. But yes, I think the multi-wavelength catalogs have spectroscopic redshifts if they're available, not just from SDSS, but like, for example, Booty's field is one of our surveys, or one of our fields, and that has spectra from the AGES survey. And so yeah, there's been a compilation of spectra that have been added to the catalogs.
Okay, thanks. Right, so it doesn't seem like there are any more questions. So thank you so much, Leah, and hopefully
thank you.
Have you here and giving another talk on how things are progressing. Lots of observational studies that you're doing. Fantastic. So thank you so much.
Thank you very much.